All right, guys, I hope everyone has had a good Friday so far. Um, you yesterday and took your quiz, and that has been graded. There's definitely some good parts to it, definitely some things I think we need to work on still. Definitely that last page with the justifications, that was really damaging to some of you, and then also that second page just kind of interpreting again like what the derivative means, what does it mean when it's positive, what does it mean when it's increasing, and things like that. I will share the key with you later today towards the end of office hours. But I do suggest you look over those quizzes. Um, we'll go over them eventually, but today I did want to go ahead and move forward with just some notes so that you did have time to look over your quizzes before I just jump in and talk about them. So today for notes, what we're going to be looking at is derivative rules. So for those of you who are much more like algebra minded, like you like solving the equations, you like dealing with algebraic expressions, this topic is going to be much more up your alley. We're not going to really do too much like graphing. There's not going to be a lot of theory behind it or conceptual things. Like it's just going to be applying a bunch of rules. And we're going to be looking at rules today. We'll learn some more rules tomorrow. But basically, like throughout this unit, we're just going to keep adding and adding more derivative rules. One thing about rules, on the AP exam, there is no formula sheet. So these rules do have to be memorized, and you do have to be able to recognize when to use them. So I did summarize if you're looking in OneNote. I do have at the very top just a summary of all your rules. So there's 2 pages of it. We're not covering all of this unit even, but there's 2 pages of rules you have to know. We'll just be covering a few of them today, the most basic ones, and then on Monday we'll kind of add on to those. But again, for those of you who are much more algebra minded, you're going to enjoy this topic a little bit more than the graphic stuff. So just to review the notation that we have 3 different notations that we use in calculus. That's kind of after the 3, in some ways, the founders of calculus. The Lagrangian notation is the one that I use most often. Is the one that is written f prime of x. The Leibniz notation again is written as dy dx. And then Newton's, his kind of is just not used, but he used the dot over y. And we know that we've talked about like the first derivative, we've looked at the second derivative, like the second derivative would be f double prime of x or d2y over dx squared. But technically in math, like we don't look at a lot of the applications of anything beyond the second derivative, but we really do have just like derivatives after derivatives. For example, you could keep going and you can say like, well, what is the third derivative? You could have a fourth derivative, and you can kind of keep going. Typically, after the third derivative, we'll put the number in parentheses because no one wants to write that many primes over and over again. We'll mainly focus our attention to, of course, just the first and second derivative when it comes to their applications. Though if you do care about fun facts, the math term for the third derivative is actually called a jerk. But we will be looking at the first and the second derivative. So I also want to look at how we can translate sentences into mathematical notation. So this first statement, if I want to translate this into a mathematical statement, I have the line tangent to the graph of f of x, which is equal to x squared, at the point 5, 25, has a slope of 10. Well, we've already learned previously that the slope of a tangent line is basically the derivative. So this whole statement can be summarized by saying f prime of 5, that's the x coordinate where we're taking the derivative, is 10. So using notation is going to be definitely helpful to us when we can summarize it. This second statement, instead of saying the derivative of f of x equals x squared is 2x, we can just shorten that and say f prime of x is equal to 2x. Likewise, if I want to say what the second derivative is, we can shorten that instead of saying a full sentence and just say f double prime is equal to 2x. And that just kind of links back to some of the concepts that we talked about, especially that first one. But what we're going to be looking at today is we're going to figure out, well, why is the derivative of x squared 2x? and y is the second derivative of x squared 2. So the first rule that we're going to have to learn is called the basic power rule. And the basic power rule is going to be described as when you have x as your base and you're raising it to a power, hence the name power rule. And the derivative of something that has a power, the original exponent is going to move down in front as a coefficient, and you're going to subtract that original exponent by 1. This is by far the most common rule we'll see when it comes to taking the derivative. So now instead of doing the derivative graphically, and I say, well, here's a graph of f, draw f prime, you'll now be able to say, here's the equation for f, what is f prime? So the example of a power rule, if I have y is equal to x to the 7th, its derivative, so that 7 is going to come down as the coefficient, and then the new coefficient is going to be 7 minus 1, giving you 6. This is also how, granted I am the calculus teacher, but this is also how I can kind of check my graphs from going from f to f prime pretty easily, because I know what equations are graphing those, and I can kind of take the derivative algebraically, which eventually you will be able to as well. So that is the power rule, and I'm just going to kind of go through a bunch of rules before we look at some examples. We also have the derivative of a constant. So when I say the derivative of c, that c is just a constant, is not a variable, so it is just a number. And the derivative of a constant will always be 0. I think this one is nice to think about graphically. So I have this equation here, y is equal to 4. Well, y is equal to 4 is a horizontal line at 4. What is the slope of a horizontal line? The slope of all horizontal lines is 0, so it makes sense. The derivative means slope. So we know that the derivative of 4 is just 0. So we have the power rule, we have the constant multiple rule. Then we also have some basic trig rules. The first one is the derivative of sine. We did this as a warm-up actually before your quiz. But the derivative of sine is actually the cosine of x. And again, the reason for that is when you go to graph the f prime when given the sine graph, it does form the cosine graph. So we have that the derivative of sine is equal to cosine. And then likewise, we have the derivative of cosine. The derivative of cosine is negative sine of x. And I do want to emphasize that negative. Often students will accidentally forget to put that negative on the graph. And again, where that answer comes from is if you use the graph of cosine and try to graph the derivative of it. All these rules do have to be memorized. I will give you a shortcut. We're not going to learn all of our trig rules right now, but one thing that helped me when I first learned these rules is that whenever you take the derivative of a co-trig function, it will always be negative. So we're not going to cover it today, but the derivative of cosecant and cotangent is also going to be negative. The derivative of all of your non-co-trig functions are going to end up being positive. Questions on any rules so far? I know I haven't done too many examples, but I know I'm also talking kind of fast. All right. Before we do some examples, I'm going to give us 2 more rules, and then we'll look at some examples. The next rule we have, I'm going to call it the constant multiple rule. And the constant multiple rule is when you have a coefficient in front of a function. And when you have a coefficient in front of a function, that function is going to carry across when you take the derivative. And then you use the derivative rule however it's going to be. So in this case, I just kind of write f prime. As an example, I have y is equal to 4 sine of x. That 4 is a coefficient, so the derivative will also have a 4 in it. And then we have the derivative of sine. Well, what's the derivative of sine? The derivative of sine is cosine. So we're kind of combining rules there. Again, this is different from the constant rule. When you have a number just by itself, its derivative is 0. When that number is acting as a coefficient, it's going to carry across when you find the derivative. And then the last rule I wanted to look at today is called the general power rule. And the general power rule is basically combining your constant multiple rule with the power rule. So in this case, this a in the front is a coefficient. The n is the exponent. So kind of using the constant multiple with the power rule, that a is a coefficient, so it's going to carry across. The n is going to come down in front, and then the new exponent, you're going to subtract it by 1. So my example is, if I say, hey, find the derivative of 5x to the 7th power, that 7 is going to come down in front. The 5 is a coefficient, so it came across. The new exponent, 7 minus 1 is 6. And of course, I can simplify that answer to give me 35x to the 6. So you can kind of see how all these derivative rules are going to eventually overlap, which is why we want to make sure we have enough practice to be able to find the derivative. In this unit, we are going to mainly focus on just finding derivatives. In units 3 and 4, basically for the rest of this first semester, we're going to be looking at applications of the derivative. So of course, you want to be able to find a derivative correctly so that you can deal with the applications correctly as well. So to give us some examples, I want to look at these 3 for now. And so sometimes we have problems, and these problems are technically power rule problems, but they're like power rule problems in disguise. So remember, whenever you have the power rule, it's going to be used when you have x raised to a number. And so we want to be able to use the power rule for these 3 problems. I think the first one, most of you can kind of see how this is going to work. If I have y is equal to the square root of x, what is that the same thing as saying x to what power? Same thing as saying x to the 1/2. So I have y is equal to x to the 1/2. Notice I'm very careful with my notation as well. I'm not saying y prime yet because I haven't taken the derivative. And then now I can take the derivative because I can use the power rule now. So that 1/2 is going to come down in front when I take the derivative. The new exponent is going to be the original exponent minus 1. So in this case, the new exponent is negative 1/2, 1/2 minus 1. You can leave your answer like that, but you can also simplify it. If you're simplifying your answer, it ends up being 1/2. A negative exponent can be sent to the denominator, and you can have x to the 1/2 in the denominator. And of course, a 1/2 is the same thing as the square root of x. All of those answers are the same. I would never say that one of the answers is more correct than the other, but you know that half of the AP exam is multiple choice, so you do want to be able to kind of move through the equivalent answers pretty easily. Questions on that one? All right.
No.
Yes, go ahead.
Oh, I said no.
Oh, no, okay. So this second one, one thing you want to be careful about when you're doing derivatives is whenever you are dividing or multiplying by things, you can't always just jump in and use a rule. For example, in this second one, this is 5/x. Whenever you have x in the denominator, you can't just take the derivative of that x in the denominator. It doesn't work that way. You want to be able to rewrite it so it looks like x raised to a power. So if I want to rewrite this one, it might help you to think of this as 5/x to the first power. How can I rewrite that problem so it's more friendly to use with the power rule? And the answer to that is I can rewrite it. I can pull that 5 up out of the denominator, not the 5, leave the 5, bring the x up out of the denominator as x to the negative first power. And the reason, again, why I want to do that is so it looks more like that power rule formula, the general power rule formula. And so now I can go ahead and take the derivative. So the exponent comes down in front. So I have -1. That 5 is a coefficient, so it came across. Make sure you always subtract by 1 for your new exponent. -1 minus 1 is -2. That is a correct answer. Of course, you can also simplify this several different ways. -5x to the -2, or negative 5 over x squared. All three of those answers are, of course, the same. And then for this last one, this one is actually easier than it looks. Again, if I'm looking at this one and want to use the power rule, I want to kind of clearly be able to see a coefficient x and then the power. So if I have y is equal to x over 5, to me this reads the same thing as saying y is equal to 1/5 of x to the first power. Dividing by 5 is the same thing as multiplying by 1/5. And of course, if we do not see an exponent there, then we know that it's going to be technically a 1. So if I'm finding the derivative of this one, so that 1 is going to come down in front. So I have 1 times 1/5, and then that's x. Well, 1 minus 1 is going to give me 0. Anything to the 0th power is 1, so this derivative is just going to be 1/5. I do think this one is nice to think about graphically as well. So if I say y is equal to x over 5, again, we're really thinking of this as y is equal to 1/5 of x. This is just a linear function. It's a linear function with a slope, and the slope of this linear function is 1/5. Well, we know in calculus that slope really is just the derivative, so hopefully that's why it makes sense to go ahead and just jump to saying that the slope is 1/5. And then the derivative is also then 1/5. Yes, Mitchell? Does anyone have any questions? I'm going to do a few more examples. I meant to add one more slide to these notes. So these are not in your OneNote, but I did want to give us just a few more examples. The first one I'm going to give is going to be x times x plus 2. And then the second one I want to give is going to be y is equal to, I'll just say 1/5 x cubed minus 4 sine of x. So I want to add these just to make sure kind of these rules are clear, and then I'll kind of take questions once I go over these two. So the first thing is we do have this thing called the power rule. We also have the constant multiple rule. What you do need to be careful with is looking at number 1, this isn't a constant multiple, this is a variable. So we can't just take the rule using the constant multiple rule. This would be an example that you want to rewrite. And how you would rewrite it is you say, oh, well, I can just distribute that x across, and that would become x squared plus 2x. Now that we don't have parentheses, this becomes a much easier derivative to take. So my derivative of that function, y prime, so I have the power rule, x squared is going to turn into 2x to the first power, and then the derivative of 2x, again, that's a linear function, and its slope is just 2. So there would be the y prime for that one. This second one, I'm going to go ahead and also add a we'll add a plus 7 at the end. Sorry, changed it up a little bit. One thing we can also do, as you saw from that first one, is that when you have multiple terms added or subtracted together, you just want to take the derivative of each part. So the second one, I have y is equal to 1/5 of x cubed. So as I take my derivative, I take it term by term. So this first term, 3 comes down in front, so I have 3/5 of x squared. This second term, that minus 4 is a coefficient. The derivative of sine is cosine. And then that last part, we know the derivative of 7, that's a constant, so it's just going to be 0. So we do see that the derivative of that function is 3/5 of x squared minus 4 cosine of x. So that is where I'm stopping notes. So at this point, does anyone have any questions on how we can begin finding the derivative algebraically? Yes, Armani.
In that first one, how did you get to the y prime again? I kind of missed that.
This first one I just did.
Yes.
So I first had to distribute this across because that's right now is not a constant multiple. That's like a variable multiple in front. So I distribute the x across. So this x squared plus 2x is the function. And I just took the derivative term by term. So I took the derivative of x squared. The 2 went down in front. 2 minus 1 is going to give you 1. So that's why that one was to the power of 1. And then the derivative of 2x, again, that's a linear function. So we know that its derivative is just its slope. So the derivative of 2x is just going to be 2.
Okay, thank you.
You're welcome. Mitchell, what's your question?
Yeah, sorry, my mic wasn't working, so
You're good.
that was kind of awkward. But it was about
One of these,
the
right?
power rule examples.
Mm-hmm.
Hello? Yeah, so that third thing you did where it said x to the 0th power is
Mm-hmm.
1. How did you get 1/5? Wouldn't that be 1? Since
This is 1/5, so the 0 is only on the x, so that's going to be 1/5 times 1.
okay, so they're not attached.
No, the 0 is only on the x portion of that one.
Okay, cool, thank you.
You're welcome. So I'm going to end notes. I did want to say one last thing. I'm not going to do it today, but I often have students say like, well, where are these rules coming from? Like, who made up these rules? And where they come from, so if I had a normal 57-minute period, I would make us do these examples. And don't like have to know this really right now, but I do want you to know like where they come from. Where these derivative rules come from is from the traditional definition of the derivative. So for example, when I say f of x is equal to x squared, and we know from the power rule that f prime would be 2x, like someone had to come up with that rule from somewhere, and where that rule comes up from is actually connecting back to unit 1 and the beginning of this unit using that traditional definition of the derivative. So if I worked out this limit, which I'm not going to right now, but this limit expression, when you work it out, is equal to 2x. So that's where those rules are coming from. Again, I just need you to be able to find a derivative, and once you know the rules, no one's going to take the time doing the limit expression for it. So your homework tonight, again, I'm not checking it till the next quiz that we have. There is a second quiz in this topic. But the homework, it is from the textbook. I have shared it with you in OneNote. It looks like a lot because it says 4 through 52, but you're only doing multiples of 4. So like 4, 8, 16, 20. So it's not that many. You can also ignore any questions about a graphing utility. All these questions are just asking you to find a derivative. Looking ahead to next week, on Monday and Tuesday, we're going to be talking about what is called the product and quotient rules. Wednesday is asynchronous, but on Thursday we'll be talking about tangent lines. Friday and Monday will be more review, and then we will have our second quiz of this unit. And I know that feels like that's coming up quick, but there is just a lot in this unit that's important, so that's why Ms. Kennedy and I kind of split it up between 2 quizzes. So at this point, I'm going to go ahead and end class. If you are good to go, then I hope you do have a good weekend, and I will see you on Monday.